all the committee and all the people working here. I will describe a little bit some work done in collaboration, especially with Goran Smiljanovic. There is one paper that we published. Actually, we sent to the net last year and published at the beginning of this year. And one paper that is we're gonna send to the net these days. But also previous work done in collaboration with Charana Olak, Alejandra Melifo, Miha Nemevšek, and Francesco Bissari. So I would like just to remind you what are GUTs. These are ground unified theories. What they assume is that the three-gauge couplings that you have in the standard model at low energy unify at some large scale. Now the exact way they unify depends on the model. So it could be, it depends on whether you assume supersymmetry or some intermediate scales or not. Anyway, what we assume is that this scale, in which all the three couplings are the same, is huge, in close to 10 to the 16 GeV. It cannot be much lower because of the dangerous proton decay. What we assume that after this MGUT, there is only one simple group, and the standard model is just a subgroup of this larger group. Of course, a bigger symmetry, a larger symmetry, typically brings new constraints and new predictions. So the first of these predictions, this is nothing new, I mean, it's just repeating old stuff, is the presence of magnetic monopoles. So the magnetic monopoles, unfortunately, in these theories, has a mass which are of the order of MGUT. So they are extremely large, and there is no hope to ever produce them in laboratory. So the only hope is that the history of the universe was such that some of these monopoles are still floating around. Typically, this is not the case. Majority of models give either too big number of protons, of monopoles. That means that such models are ruled out, and this is the so-called monopole problem. Or they give a very small number of monopoles today. These are typical predictions of low energy inflation. The second prediction is the proton decay, and these are searched in superchemicality, unfortunately not found yet. Anyway, they can give some constraints on the parameters of the model. And the third, let's say, check of ground unified theories are fermion masses and mixes. And this is the issue I will consider today. Now, in standard model, for MSSM, we know that the charged fermion sector has UCAVAs, which are not related. So they must just fit the data, but in general they are 3x3 complex matrices, and there is no relation between them. I mean, not from the standard model. Of course, neutrino in the standard model is massless, a 3 order, if you assume only renormalizable couplings, and the first operator that breaks this, that is non-renormalizable and can give mass to the right-hand neutrino, actually not to the right-hand neutrino, to the neutrino, which is my Rana type, is of this type. Okay? So here you have another UCAVA coupling, which however is symmetric, but otherwise completely general, any 3x3 complex symmetric matrix. The only thing we know for sure is that M is large because the neutrino mass is so small. And this is a form of the matrix which is automatically implemented but in the seesaw mechanism. So if you integrate out a heavy standard model singlet, for example, a neutrino, this type of operator is the seesaw type 1, or another possibility is to integrate out a heavy triplet, SU2 triplet, and this is a famous type 2 seesaw. So the question is, okay, why should a ground unified theory be better? Why should predict these UCAVAs? Well, first I will consider SO10, not general ground unified theory, but SO10. The reason for that is that in SO10, the minimal representation, the representation in which you can fit all the fermions of the standard model is a 16-dimensional representation. So you automatically also introduce a right-hand neutrino, which then you can use for the seesaw mechanism. So SO10 is a theory of neutrino masses.
Theory of seesaw mechanism means the spotting of the mass have the one is very small.
Yeah, the one is very small, the other is very, very large. So you can actually, the reason for that, the reason for that is that they mix, but one is, its mass, Majorana, is very large, so when you integrate it out, you give a tiny mass to the other one, because of mixing. But exactly, seesaws, because one is very large, this is right-hand neutrino, and one is very small, this is left-hand neutrino. The one that we are looking in superchemical. So, anyway, you can see that all the fermions, and so we have 3 generations of them, live in the same representation. So clearly, one could expect that there are some relations about these low energy parameters. Of course, these relations are, however, can be found out only at the gap. Then you have to run down to compare with data. So, before continuing, I would like just to remark, recall you what I will assume. So first, I'll consider only SO10 case symmetry and no flavor symmetry. That's because in this case, there is, it's much easier to find out what is the consequence of a gauge theory, of course. And also, it's less model dependent. The second thing, of course, that I have to, however, assume is the normalizability of the theory, also of the ground unified theory, because without that, and without flavor symmetry, there's no hope that I can find any relations. So the need for predictions forces me to consider ordinary normalizable operators. I would like to recall you, however, that this is not so crazy because we know, for example, one example in which we are forced to neglect this non-normalizable operator because of phenomenological reasons. So it could be possible that for some strange reasons there are no 1/n blank suppressed operators. Anyway, I will assume that there are none. Now, to see what are the possible UCAVAs in the SO10 model, you just need to consider what is the...
Yeah. Are you going to make any predictions that... I always thought you could just ignore the 1/n blank operators because they were irrelevant, so I wouldn't have even talked about them, but you're making an important point.
Oh, no, they are not irrelevant in the sense that 1/n blank, if you consider a ground unified theory, this is the correction is of the order m/n blank, which is 10⁻⁵. If you consider UCAVAs, for example, the first generation UCAVA, these are 10⁻⁵. So actually, it's not. I mean, these operators could be very dangerous. Not dangerous in the sense that they would not. They would spoil any prediction. There are so many of them that I cannot say anything after that. So I have to assume that for some strange reason that I don't know, they are negligible. So what type of UCAVAs I have in a SO10 GAT. In completely general, if I do a completely general analysis, I can see that the 16 square is just 10 plus 120 plus 126. So I have just three possibilities for the Higgses that give a mass to our fermions. So the most general UCAV is of this type. Of course, if you want even to complicate even more, you can consider more than 110, more than 120, or more than 126. And remember that these are 3 by 3 matrices, because we consider 3 generations. And SO10 restricts me to symmetric 10 and 126 UCAVAs and antisymmetric 120 UCAVAs. Clearly, the most general, such a term is not restrictive at all, and I should now consider subcases in which some of them are present and some not. For example, let's first of all see the oldest example known in the literature, which is just the presence of one 10-dimensional Higgs representation. Now, in seeing what we get from this term, it's useful to decompose each representation in terms of the Patti-Salam SU2L cross SU2 height cross SU4 color. In this decomposition gives, for 10, gives a 2 to 1 and a 116. Now this 116 cannot get a value because it doesn't contain any standard model signal. These 2 to 1, however, are just the bi-doublets. So these are 2 doublets, standard model doublets, so they can pick up a wave, and they contribute to the masses of these light fermions. There is, however, a problem here that we don't break SU4 color. That means that since the 16, the fermionic 16, is decomposed in the Patti-Salam as 214 plus 124 bar, and 214 is this object. You see, this is the SU4 color direction, and this is the SU2 left direction. You see, if you don't break SU4 color, then there is no distinction in this direction. So obviously, the down quark mass matrix is completely the same as the charge electron mass matrix. And also the same is true for the up quark mass and the direct neutrino mass. So in short, the predictions are the following, if you consider only one 10-dimensional Higgs. You get that MB equals n tau. This is a good prediction. Remember that this is valid at MGAT. And typically, when you run down to our energies, you will get the correct relations. However, the same relation for the second generation, strange quark equals muon mass, and down quark equals electron mass, they are bad. When you round down, they are bad. Also, since you have just one matrix, UCAVA matrix, you can always make a unitary transformation in generation space such that you diagonalize this UCAVA, the only UCAVA matrix that you have. So you cannot have any mixing in this type of example. Well, this, I cannot say whether it's good or bad. I mean, the quark sector is quite good. It's a good approximation that the quark mixing are small. However, in the neutrino sector is very bad, since neutrino have a large Dirac mass in this model, and no mixing at all. Now consider next the 126-dimensional Higgs. Now the same decomposition, the Patti-Salam subgroup, leads to different possibilities, and you can have 3 different types of X. One is the triplet FET, SU2 triplet FET, that can give contribution to the type 1 system. The second one is the contribution to the very big right-hand neutrino mass. And of course, in the seesaw, when you consider then a seesaw, this will be suppressed by this mass. So that's why the neutrino mass at the end will be small. And the third contribution is the contribution to the Dirac particles. And remember now that instead of 2 to 1, you have a direction 2 to 15. That means that you break as in for color, and you break in the D minus L operator, 1, 1, 1, minus 3. That means that leptons, which live here, will experience a minus 3 time the coupling to the quarks. So 3 times bigger coupling. Okay? So the predictions are, because of that, you have that the tau quark in such a model gives you a 3 times bigger mass than the bottom one. Of course, this is a bad relation. However, it's very good in the second generation, and again bad in the first. Okay? No mixing, that's as usual. And in this model, however, neutrino are Majorana particles. And the seesaw mechanism nature. So again, you see, you have some good relations, some good predictions, and some bad predictions. Now, the third possibility is the 120-dimensional Higgs, and this is apparently the less interesting, because apparently, you see, you cannot give any mass. I mean, you have 2 types of doublets that can give contributions to the Dirac masses, and one is in the 2 to 1 direction, and one is the 2 to 15. Now, the interesting part is that Yukawa 120 is antisymmetric, so the number of doublets is small because of that. But because of that, a single Yukawa 120 gives quite bad predictions, in the sense that the eigenvalues are just plus A minus A 0. There is no restriction among different masses, because of this you have 4 doublets actually. So you have completely different numbers here. There is no connection between these different pairs. Of course, no mixing, and neutrino again is of Dirac type. So let me just, before continuing, summarize what we learned from this short review. The 10-dimensional Higgs gives a good prediction that the third generation down quark mass and charged lepton mass equals. The second prediction is from 126 that I didn't mention, but 126 breaks rank, and this is because you need that to give a mass to the right-hand neutrino. So this is a good prediction, and a good prediction is the second generation relation. 120 apparently seems not very promising. That's why people try to consider first, in order to find a realistic model, to consider just these 2 Higgses, 10 and 126 dimensional Higgs. And this model has 15 real parameters in the Yukawa sector. 3 because you can diagonalize the 10-dimensional symmetric to Yukawa 10, and then you are left with a symmetric, completely general symmetric complex 3x3 matrix, which has 6 complex parameters or 12 real. So altogether there are 15 parameters to fit. And it was found out that model is compatible with data. I mean, you can really fit all the data you know, and you also predict some data that you know, you don't know, and you are going to measure maybe in the near future. There's also some interesting understanding of why we have a large atmospheric angle. Actually, what you can understand is that in type 2 seesaw, if type 2 seesaw mechanism dominates, then there is a nice relation between V tau unification and large atmospheric angle. And I think maybe it's worth to show it. The reason is that in type 2 CISO, the left-handed neutrino is proportional to the Yukawa 126. Now, however, we know that the Dirac and the charge lepton mass matrices, not Dirac, sorry, the down quark and charge lepton mass matrices are given in this model by two contributions. The first one is the 10-dimensional contribution, the other one is 126-dimensional. Remember that in 126 there is a 2 to 15 that gets a bad, and that's why there is this -3 factor. Okay? Now, it's trivial to find out that the difference of these two matrices is nothing else than Yukawa 126. So, in other words, the neutrino mass matrix equals the difference of these two matrices. So, in an approximation in which you take only the second and third generation, and you neglect the second generation masses, which is experimentally a good approximation, what you find out is for small mixings, actually this is just to understand the idea, actually you can do much better, is that this mass matrix is proportional to a matrix which has only one non-zero, actually three very small numbers. These two are mixings. This one is small because the masses of the second generations are small, so you get MB minus N tau here. So the only way to get a large atmospheric angle is to unify B and tau. Okay, so at large scale, or gas scale, you need beta unification if you want large atmospheric angle. So, and since this is a good numerical is quite good, you have a sort of prediction that the atmospheric angle is large nature.
So you neglected these 1/Planck scale operators. They only affect the first generation, or do they affect the first two generations?
The second Yukawas are 10 to the -2 to 10 to the -3. So they could be a little bit affected, in principle. But only if the numerical number is 1. Because if you have 1/Planck, it will not be suppressed most. Now, up to now it was, let's say, the usual stuff. Now I would like to really enter into the main topic. And this is this 126-dimensional Higgs really necessary? I mean, apparently it looked as it was necessary because it was able to break rank, to give mass to the right-hand neutrino, and so on and so forth. However, imagine a theory in which you consider, instead of 126-dimensional Higgs, you consider 16-dimensional Higgs. This is enough to break the rank. It's there with the SU5 singlet direction, says the scale of the SU2R break. Now, apparently, such a model doesn't have any mass at 3 order because 126, there is no 126. And there is no coupling of the 16-dimensional Higgs to the fermions. So one can use the emittance idea in which such a mass term is generated at 2-loop level. Okay? And it's proportional to the Yukawa 10, because you have here the Yukawa 10 is the only Yukawa that enters. You have MR square, which are the rest of the two 16s, and 1/m, because it's just for dimensional reasons. And alpha/pi is the suppression factor due to 2 loops. Now, when is this valid? Of course, in the beginning of the 80s, that could be valid because the running was a little bit different. So now we know that in non-supersymmetric models that is difficult to work without any fine-tuning because MR should be lower than MGAT in order to unify the 3 couplings. So MUR would be too suppressed. In supersymmetry, we know that there are no such corrections, because at least for low energy supersymmetry. The only possibility is presented by the split supersymmetry scenario, in which, as you know, Genus and Xeno live at the TV, in the TV region, and there is an MT that says the scale of the Fermion masses. Now, in the original Arcanic Dimopoulos paper, there is no real argument what this M tilde should be. Now, however, you find out that if M tilde equals M gut, then you get exactly the right scale in which the Witten's radiative mechanism works. Of course, the Witten's model is too simple. Not because, I mean, it gives that the neutrino mass is proportional to the Yukawa 10, but and it gives a good NB equals M tau, beta unification. However, there is again no mixing. Mu equals Ms and M equals Md. So what you need to correct the low energy Dirac masses. So our idea was add another 120. You don't want to add another 126 because then you do double counting there. So add another 120. Why 120 is also very appealing because it gets a low number of new parameters. So altogether, the Yukawa sector has only 3 plus 6, 9 real parameters. Remember, before we had 15. Now, okay, of course, when you write down the equations for all the fermions, you get different contributions. The first column is due to 10-dimensional Higgs, and this is due to the 120-dimensional Higgs. The important point is that I will rewrite these equations for the Dirac masses in this form. Now, even that this form is quite hard to solve in a general, because you have many parameters. But before doing that, it's very useful to see if you can find a subsystem in which you can study maybe analytically. So the idea was study first the second and third generations. In this case, of course, M0 is just diagonal. You take this basis, and they are real. You can choose them real. M2 is so simple, it's like proportional to sigma 2. Okay? So altogether, you have 11 parameters to fit. And still, it seems that there are a lot of parameters. But you can find out that actually very few of them are relevant. Now, what makes life easier is to neglect the second generation masses. And what you find out that in such a simple model, you predict 3 different things. First, beta unification. In spite of the fact that you don't have only the 10-dimensional Higgs, but also the 120-dimensional. Second, if the atmospheric neutrino angle is maximal, then you predict that the quark angle is small. This is quite remarkable. And third, another important thing is that in this type of models, if this atmospheric angle is maximal, the neutrino must be degenerate, or almost degenerate, of course. How much? 1 minute. Okay, so I won't prove. The proof is actually very simple. It's 2. But, so, okay, let me just summarize then. What I considered was the Witten's idea of radiatively generated right-hand neutrino mass, and we added to that the 10-dimensional and 120-dimensional Higgs representation to correct the relations of the Dirac masses. What we concluded is the following. First, this is even if the system was very simple, it's a counterexample to the claim that granular theories usually want hierarchical neutrino masses. Second, the quark mixing angle was small here because it comes out as a difference of two large angles, while the leptonic mixing angle is large because it fails to cancel. In fact, okay, I didn't have time to show, but in fact, the leptonic ones, the neutrino angle is actually 0, and all the angle is due to the charged lepton. It comes from there. And the fourth prediction is, as I said, beta unification is automatic in spite of the presence of the 120 dimensional case. So that's all.
Any questions?
Can you remind me what is theta Q experimentally?
Theta Q experimentally is 4 times 10 to the minus 2, but that is at MZ. I'm talking about, and that, of course, the new.
Theta is not under.
No, but it's 10 to the minus 2, few times 10 to the minus 2.
Next.
You said you had to neglect dimension 5 operators. Is that just because of fast proton decay or because of something else?
No, because you see, if you can restrict the number of different Yukawas if you consider only renormalizable couplings. If you have higher dimensional operators, then of course you have other Yukawa couplings. And of course, all the predictions are gone because then you have too many Yukawa matrices, and then you cannot really predict anything.
It's not just the proton decay.
No. These are not that type of 5-dimensional. These are just the, let's say, 1/n suppressed operators.
Does your theta Q stay small if you take the first corrections in the ratio of the mass that you set to 0? I mean, those.
Yeah, that's a good question. That's a good question, actually. What I can tell you is that similar analysis, 2-generation analysis, can be done in the 10 plus 126 dimensional case. In that case, more or less, you find the same results if you consider these corrections or not. We didn't do that for this case yet. But it's a good question because sometimes exactly the angle can be very sensitive to that. Yeah.
If there is no questions,